Hi, the title of my presentation is Power Quality Considerations in the Planning Phase of Standalone Wind-Powered Microgrids. There has been and will continue to be a rapid rise in the use of nonlinear loads in residential load profiles, which not only highly deteriorates power quality, but also reduces power factor considerably. At the same time, wind power generation systems are reported to be another source of harmonic contamination, especially the third, fifth, seventh, and ninth harmonic orders. So, an integrated approach is required to eliminate both the wind power voltage harmonics and load current harmonics, and that is of prime importance in standalone wind powered microgrids. The shunt active power filter is a mature technology to mitigate the adverse effects of the load current harmonics. However, it is not capable of suppressing the harmonics induced by wind turbines. So, in their groundbreaking study of 2012, Rahmani and Talakolibina proposed an advanced universal power quality conditioning system, or AUPQS, to address such inefficiency of basic shunt active power filters. The UPQS integrates a shunt active power filter, a series active power filter, and active rectifier. They also put forward an advanced generalized theory of instantaneous power to optimally control the UPQS and demonstrated its effectiveness in mitigating the negative effects of load current and wind turbine voltage harmonics. So we've used their method for the compensation of load current harmonics under non-ideal conditions of voltage waveforms produced by a wind turbine within a standalone microgrid. So basically the contributions of this research were threefold. Firstly, we proposed a resilient power quality aware microgrid system structure to transition Stewart Island in New Zealand to 100% renewable energy independence. Secondly, a multi-criteria sustainable energy investment planning modeling framework is proposed to minimize the whole life cost of microgrids in conjunction with maximizing their power quality. And finally, we've highlighted the significant impact of power quality considerations on the estimated total discounted system cost. This schematic shows the configuration and power flow of the microgrid system proposed to be implemented on Stewart Island in New Zealand. This standalone microgrid is equipped with a wind turbine power plant as its sole generation unit, a hydrogen backup system consisting of a fuel cell, which converts the surplus power to hydrogen, which is stored in a hydrogen reservoir for use at times when wind generation cannot entirely meet demand. And a supercapacitor bank is also considered to serve the transient power required by loads. And this is the AUPQS system used to address harmonics, as mentioned earlier. An AC dump load is also considered to dump the surplus generation when the storage units are full. This is the power curve of the selected 100 kilowatt wind turbine, and this figure characterizes the percentage of the total harmonic distortion of the injected power by the 100 kilowatt wind turbine at various wind speeds with system frequency of around 50 Hz. So the case study site is Stewart Island in New Zealand, whose current power supply scheme for a population of around 400 is totally based on diesel generators operated in a centralized manner. Now, the proposed by objective microgrid investment planning model consists of two conflicting objectives. The first is the total net present cost of the system, or the whole life cost of the system, which is the sum of the net present costs of the microgrid equipment, namely the wind plant, electrolyzer, hydrogen tank, fuel cell, supercapacitor bank, and a UPQS system, which is used to mitigate harmonics. And the net present cost of each component equals its optimized capacity, represented by N, which is multiplied by a term that includes the capital cost, replacement cost, operation and maintenance cost, and salvage value of the component. And also two factors are used in this term to account for or adjust for time value of money, which are functions of the interest rate, the component lifetime, and the total project lifetime. And the second objective is to minimize the whole system harmonics distortion level, which is used as an index for power quality. In this equation, N is the total number of nodes with power quality issues, which equals 2 in our case. And to use this index in the planning phase of microgrids, we've adapted this index to account for all the hours of a year-round load profile. And the optimization problem is subject to a reliability constraint defined by the loss of power supply probability technique, which can be expressed by this constraint, where P sub and P dim respectively represent the supplied and demanded power at time step I. As the input data, this figure shows the monthly average 24-hour profile of the forecasted load demand. The wind speed profile is also forecasted by averaging the 10 years from 2009 to 2018 historical data collected for the case study site at intervals of 1 hour, and the monthly average daily profile for it is shown in this figure. Also, the techno-economic specifications of the microgrid equipment are presented in this table. For example, for the UPQS device, which is used to suppress the load current and wind turbine voltage harmonics, the capital cost is $2,800 per kVA. The replacement cost is $2,600 per kVA, and the operation and maintenance cost is $52 per kVA per year, and the lifetime is 20 years. And the modeling, optimization, and analysis of the conceptualized microgrid system were carried out using the MATLAB software. As the multi-objective optimization algorithm, we used the non-dominated sorting genetic algorithm 2, or an SGA2, to find the Pareto optimal set of solutions for the problem at hand. For example, this is the Pareto optimal frontier obtained by the NSGA2. And for example, for the case where no harmonic suppression mechanism is conducted, this point, the whole system harmonics is found to be around 19%, and the total net present cost of the system is around $6 million. And on the other hand, for the case where the harmonics are fully at rest, the total net present cost is rises to around $8.6 million. And we also used an interactive fuzzy satisfying approach to determine the best compromise solution out of the Pareto optimal non-dominated solutions. And to this end, we impose an additional constraint to delimit the maximum level of the whole system harmonics distortion level to 5%. Accordingly, this point was found as the utopia point at which the whole system harmonics distortion level equals 1.96% and the total net present cost of the system is around $8.2 million. Also, this table shows the optimal combination of the size of the microgrid equipment at this utopia point. So we found the optimal quantity of the wind turbines and the supercapacitors to be 26 and 9,415 respectively. The optimal capacity of the electrolyzer was found to be 1,391 kilowatts. The optimal size of the hydrogen reservoir was found to be 853 kilogram. The optimal size of the fuel cell was found to be 320 kilowatts, and the optimal size of the AUPQS device was found to be 621 kVA. Plus, we found that the power quality improves from 0.810 to 0.994 by integrating the AUPQS device into the proposed microgrid at the best trade-off solution. Okay, last slide. So we proposed a bio-objective decision-making modeling framework which involves trade-offs between the whole life cost and power quality of a conceptualized wind-powered microgrid feeding nonlinear loads to be installed on Stewart Island in New Zealand. To this end, we used the AUPQS apparatus, which integrates a shunt active power filter, a series active power filter, and an active rectifier to compensate for harmonics generated by nonlinear loads and the wind turbine power plant, and which is controlled using the ICHQP theory. This is a big deal. The findings of this study support the idea that devising appropriate power quality improvement schemes in the planning phase of renewable energy systems is of prime importance for more realistic assessment of their costs and consequences. And the findings of this study are transferable to other case study sites and can be improved by accommodating other sources of harmonics such as those caused by plug-in electric vehicles. Thank you for your attention. If you've got any question, I can be contacted directly at soheil.mohseni@vuw.ac.nz. Thank you.